Okay, so today we're going to start the review of Unit 3, which is on circles. And so we are skipping right triangle trig for the moment, even though we're going to refer to it for just a second today. In your textbook, Unit 3, so those of you that are going online to look at your textbook, you would start it on page 351 because that's where Unit 3 starts. In your textbook, Unit 3 is volume and surface area of solids, and then also circles, all things circles. Okay, so the big ideas of the first section are on circumference and area of circles. So when we're dealing with circles and we're looking at circumference and area, if you're given one and asked for the other, what those two formulas have in common is the radius. So you would solve for the radius to switch in between the two formulas. Now, this does make this math teacher a little sad, but I snipped this right off of your formula sheet. You guys all have a copy of your formula sheet. So do you see that you are given the area of the circle? Do you see that you're given the formula for circumference in terms of diameter and circumference in terms of radius? Makes me a little sad that they put all this on there. I think there are certain formulas that when we get to higher level mathematics you should be required to know, but they're there. They also put the area of a triangle formula on there for you. Yes. Yeah. So you don't have to memorize the formulas if you haven't already done so, even though I believe you should. And you just have to be able to apply them. So they're probably not going to give us a straightforward question. It's probably not going to say, the radius of a circle is 2 inches. What is the area? Okay? It's probably going to be something more like, the distance around a circular koi pond is 12 feet.
A koi pond. Why is it always a koi? Yeah. I've seen that on so many problems.
Are you serious?
Yeah.
I just randomly picked koi.
I've seen that so many times.
Okay. So the question would be, the distance around a koi pond is 12 feet. If you are building or if you are designing a tarp to cover the koi pond from the sun, how many square feet of fabric would you need? So it would give you circumference, the distance around circumference. So if we said it was 12 feet, we would set that equal to circumference, which is 2 pi r, and we would divide by 2 pi. So we could leave it like this for the exact answer, and then area is pi r squared. So we could punch this right into our calculator and get the approximate square feet. So 12 divided, I could leave this as 6 divided by pi squared. Now we can't cancel the pi's, can we?
No.
Because this pi is being squared and that one's not. And that's how you would solve that problem. Okay, everybody punch it in, make sure you can do it. And this week we are only practicing with EOCT, allowable calculators. Okay?
What are we doing?
Okay, and you should get approximately 11.5 square feet of fabric would be necessary to build a shade over the top of the koi pond.
6 divided by
I want to pentagonal koi pond.
Oh, good, because we're about to do the area of a regular polygon.
I got it.
Okay, so like I said, probably won't be straightforward. It'll probably be in terms of a word problem like I just gave you, something like
I
that.
promise they always use koi ponds then.
Okay, you let me know after you've taken the end of course test if there was a koi pond problem.
The entire
Okay.
test is about koi ponds.
Just every
How
column.
much volume does a koi
Well,
pond
we
hold?
could turn that into the volume. If we said that the koi pond was 8 inches deep, what is the volume of the water? We definitely could. All right. In the first section from this Unit 3 in your textbook, it also talks about the area of any regular polygon. What does regular mean?
Not irregular.
Okay, you're not wrong.
As a fraction.
It means all sides have the same length and all angles have the same measure. So when we talk about regular, that's what we're talking about. And to find the area of any regular polygon, I know we really didn't focus on this much at all last year,
Don't know what.
but I do want to go back over it. It's 1/2 the apothem times the perimeter.
So with,
Okay, now let's talk about what apothem is. Apothem is the perpendicular distance from the center of any regular polygon to a side. Now, this is not clearly stated as a standard, but the next thing that is a standard is finding the volume of prisms and the volume of pyramids. And we could have a hexagonal base for either of these, or a pentagonal base, or an octagonal base. So if you don't know how to find the area here, then you wouldn't be able to find the volume here. So, once again, not certain that this will be on your end of course test. They may just give you a rectangular prism, which means the bottom is the base is a rectangle. They may not give us a hexagonal prism. But this is what you would do if they did.
Now, we're going to have a big formula sheet on our test?
Okay, all of these right here, I've already handed you the formula sheet.
Yes, ma'am.
Okay, everything typed right here,
Is-
I snipped directly off
But
the formula
we get to
sheet.
use that formula sheet on our test?
They will
Exactly.
hand you a new clean one
Okay.
the day of the test. So you can't use the one I gave you to study by, but it should look exactly the same.
Aren't we going to be in here when we take it?
You will.
Okay.
I will not be in here with you though.
Oh.
Thanks to some schools that weren't always quite so honest.
Oh.
2 years ago.
Um, we will be switching rooms. Teachers will. You guys will be in the same
We get
place.
Miss Collins instead of clothes.
I'm not certain. I did look at it this morning, but I didn't memorize who would be in here. Another math teacher should be in here. But you will be in here, so you'll have access to the calculators that we've been using all year long. Okay? All right, so it's 1/2 the apothem times the perimeter, and the apothem is that perpendicular distance from the center of a regular polygon to its side. So how would a problem like this look? They might tell us that a regular hexagon has a side of 12 centimeters and to find its area. So if we thought about a regular hexagon, I drew it in. Do you see it? I can draw in 6 little congruent triangles in there. Because it has the 6 sides, it makes 6 congruent triangles. And all the way around here would be 360 degrees. All the way around. But this central angle right here would be what? 360 divided by 6, which is 60. Good. Now that is helpful because if I know this whole thing is 60, if I draw down a perpendicular, I've now created it bisected here, so it turned this into a side of, instead of 12 all the way across, halfway is 6. It bisected this angle, so instead of 60, it is now 30. So what I just created was a 30, 60, 90 right triangle. Okay, that's one of our special rights. We could also use right triangle trig since we'll have our calculators that day. And so to find the apothem, you can either remember we're multiplying by the square root of 3 because that's the long leg. And we would say this is 6 root 3. Or if you didn't remember that and you had to use right triangle trig, you would say tangent of 30 is equal to opposite over adjacent, which is the apothem. So the apothem is going to be 6 divided by tangent of 30. All right, so now we know the apothem. And if one side is 12, what would we multiply that by to find the perimeter? 6. So the area equals 1/2 the apothem, which we could either use this if we didn't remember special rights, times the perimeter, which is 6 times 12. So the exact area would be 216 root 3 centimeters squared, right? Because half of 12 is 6, and 6 cubed is 216 root 3. Okay? Yes, Carter?
Does it matter how many sides the polygon has, or does that work for any number of sides?
If it were a pentagonal, instead of dividing by 6 here, we would divide by 5, so it would be 72 degrees. So when we drop down, it would be half of that. So this angle right here would be 36.
Okay. But other than that,
So we'd have formula number 10.
Yeah. If it were octagonal, we would divide by 8, which would give us 45. Okay? So it does depend on what type of regular polygon you have, yes. All right. And then what did we move on to? We moved on to volume. Well, look at this. This is where I snipped it off of your, this kills me. They gave us all the formulas, didn't they?
They did.
So, we just need to remember what they mean. So if we're finding a volume of a prism or a cylinder, either one, prism or cylinder, it's the area of the base times the height. So we have to be able to identify what the base is. Okay, so let's look at this one. What is the base?
The area of that triangle.
Okay, so the base on this one is a triangle. So we would have to do 1/2 the base of the triangle times the height of the triangle times the height of the prism. So we have two different heights. One's the height of the triangle, one's the height of the prism. Do we see the difference?
Yes.
Okay, what is this?
Pentagon.
It's a pentagonal prism. So it would be the area of the base, which is 1/2 the apothem, times the perimeter, times the height of the prism. Now, do you see how they laid this prism on its side? The height is going to be on the side.
Oh, tricky.
They can lay it on its side. Are you able to tell what the base is? The base is the two faces that match exactly. That's your base. All right, so this is a cylinder. Same formula, area of the base times the height. Well, the base is a circle. What's the area of the base?
Pi r squared.
Pi r squared times h. So it's big B times h, but big B represents the area of the base. So that's going to change depending on your type of solid. Okay? All right, so how would they give us one of these types of problems? I really think they'll involve several things with it. So let's say they tell us that the circumference of the base is 10 pi centimeters. And the height of this cylinder is twice the radius. Find the volume. So it's not extremely straightforward, is it?
No.
But we have all the tools we need right here to find it. So circumference equals 10 pi. Well, circumference is 2 pi r. So what is r if circumference is 10 pi? 5. In this case, 5 centimeters, but I dropped the unit here. So 5 centimeters. So we're plugging in 5 here. And it says the radius, the height is twice the radius. So what is the height? 10. So 25 times 10 tells me I have a volume of 250 pi centimeters cubed. Volumes measured in cubic units, area in square, any length in plane units. Okay, so we see how that could happen. It's also probably going to be in terms of a word problem. So, take a look at the examples in your book. Now, do you remember Cavallari's principle? And we talked about this last year. We took a stack of CDs and I tilted it. And we noticed how the height of the CDs didn't change when we slid them over to the side.
We did not do that.
Y'all didn't do that.
Never heard of it.
Okay, I've already put up my stack of CDs, so we'll pretend. We'll go with my stack of floppy disks.
Floppy disk.
Okay, so this is my stack of floppy disks from mid 2000s. All right. So there's a stack, and it has a volume. Am I changing the space that this takes up if I slide it over? No. Still
Just
takes up the exact same amount of space.
Staggered on the edges.
Did I change the height of it when I slid it over?
Yes.
Oh, you think I did?
Oh no.
I did not.
Isn't it? It looks staggered though. It looks like it would be bigger.
She didn't add anything to it. It's still the same stuff.
Okay, so the height goes to right here. Alright, there's my height. Close enough, anyway. Alright, so if I tilt it, I like to use a book to make it tilt perfectly, but I'm not. Did the height change? No, height's the same. So Cavallari's principle was that even if we have a solid that is slanted, the height is going to remain the same, and the volume is still the area of the base times the height. Okay? So on this slanted cylinder here, we would still do the area of the base times the height of that cylinder. But the height is not inside the cylinder, is it? It's actually outside. It's perpendicular to the base. Okay? All right. That's good. All right, so now let's talk about pyramids and cones. And once again, they give us the formula. Very nice of them. All right, so we know it's a pyramid or a cone if it comes to a point. So here we have a pyramid, and I've told you that this is I'm about to tell you, that this is a square pyramid. If my baby will cooperate, I'll even write it. It's a square pyramid, which means its base is a square. And all sides of a pyramid, the lateral faces are always going to be triangles, right? So this is a square pyramid. And to find the volume of any pyramid or cone, it is 1/3 the area of the base times the height. Do you guys remember last year we watched the video of the guy pouring the water? And it took 3 of them to equal to 1, so we knew it was 1/3. Okay, this year we actually did it with water because I got this new cool set, and it didn't have holes in it, and it held water. Yep. Okay, so here is our pyramid, and you're given the slant height, which is the height on one of the faces. And you're given that the base has a side of 10 inches, and asked to find the volume. So here's a problem, but it's not straightforward. Because we currently don't have the height of the pyramid. We have the slant height. We have the height on one of the faces, but not the height of the pyramid. But do you see where I've highlighted right here?
Right triangle.
That turned into a right triangle, didn't it?
It did indeed.
And the slant height has a height of 13 inches. And all the way across the base is 10 inches. So what would halfway across be? 5 inches. So what would the height of the pyramid be? Oh, this is one of our Pythagorean triples.
12.
Good. 12. It's a 5, 12, 13. What were our Pythagorean triples? 3, 4,
I don't
5 and 5, 12, 13. These are the two that the SAT loves.
And any multiples.
And any multiples of those. So 6, 8, 10. 10, 24, 26. 9, 12, 15. Any multiples. Good. All right, so the height of this is 12. And the base has a side of 10, so the area of the base would be 10 squared. So the volume would be, well, 10 squared is 100, and 3 goes into 12 4 times, and 4 times 100 is 400. So the volume is 400 cubic inches. Okay, definitely could be in word problem form though, guys.
Egyptian pyramid.
Yes, there we go. Okay, now the second one I have here is a cone, and we did a problem this year that was pretty cool. The next thing we're going to talk about is a sphere. And so we did a problem that said the volume of a scoop of ice cream is, and if it melts completely, it fills up the cone. If the diameter of the cone is this, what is its height? Isn't that good? Yeah. Okay, so we would solve for the radius and then plug that in and then get the height, right? All right. But let's say we just had this, 2 cones. And if the radius and height of my first cone is doubled, which it's not, let's just pretend, what's the effect on the volume? How many times greater would the volume be? What do you guys think? Twice as big? 4 times as big? 8 times as big. Good, you saw my answer. All right, so if we double the radius and the height, how does it change the volume? Well, let's plug it in. This is the original, and if I double the radius, and if I double the height, how does that change my formula? Well, it puts, when I square this, I get 4r squared times 2h. Do you see that this makes 8 times the original? So if I tripled the radius and the height, how would it change? 27 times. What if I just tripled the radius and did not change the height? 9 times. Okay, so do you see how you're just plugging that in and seeing what the net change is from your original formula to your new? Could you do that? All right. How would we find the volume of a cone? Well, the base of a cone is a circle, so it's that pi r squared h. That's where that formula came from. Because the base is a circle, that's where we get the pi r squared from. So volume of anything that comes to a point, pyramid or a cone, is 1/3 the area of the base times the height. Are we good? Okay. Sphere. All right. So sphere, volume is 4/3 pi r cubed. Now, what we need to remember about a sphere, do you guys remember the great circle? Okay, a great circle of a sphere is just a circle whose center is the same as the center of the sphere. So we can have an infinite number of great spheres, but you can see this one. I'll highlight it real quick. You can see the one that I used right here. Here is a, oh, that is an ugly highlight color. There's a great circle. That's just so unattractive. I'm leaving it though. Okay, so let's say I told you that the area of a great circle is 100 pi square feet. Find the volume of the sphere. Okay, so 100 pi square feet. Volume of the sphere. Well, we know this is area. So I set area equal to pi r squared. So what is r? 10. And then I plug it in. 4/3 pi r, whoops, that's feet, cubed. So it would be 400 pi feet cubed. Now, if you got that on your calculator as an answer, and what if they had all the answer choices in decimal form? What would you do?
Multiply.
Press the little approximate button. Where's the approximate button? It's directly above the enter. And that takes it from exact form, which it was, that's what it always tries to give you, is exact form, into the decimal approximation. Okay? Now, if we wanted volume of a hemisphere, it's just half the volume of a sphere, so it'd be 2/3 instead of 4/3. So half of 4/3 is 2/3. And then surface area of a sphere is 4 pi r squared. Now, I don't think you're given hemisphere, but we ought to be able to deduce that. Hemisphere wasn't on there, was it? No. But we can do hemisphere without being given the formula. Okay. Any questions about spheres? Okay, there'll be some questions for you to practice about volume and surface area. And they did give us a good number of formulas on our formula sheet. You are given all of this. You do not have to memorize it.
So we can use the formula sheet?
Yes,
Okay.
they will hand you. Actually, I think the formula sheet is in your book.
Built in.
It's built into the book.
Section.
Okay.
On the first section, the formula sheet is at the beginning of the book. And the second section, there's another formula sheet at the end because you can't flip back and forth. So it is in the book. Flip to it if you need it. Okay. Now, let's talk all things circles. This is like a mini geometry unit. Okay. So, here is a picture. And let's talk about what all these things mean. It looks like I overshot a couple of them. All right. If a segment connects 2 points on the circle, it's called a chord. If that chord happens to pass through the center of the circle, it is a diameter. And the diameter, any diameter, is the longest chord of the circle, right? Okay. A segment that connects the center to a point on the circle is called the radius. And then we have two types of lines that exist not only inside the circle, but outside as well. And one is the secant. A secant passes through 2 points on the circle, versus a tangent touches in exactly 1 point. And where it touches, it is perpendicular to the radius at that point. So if we have a tangent, it's perpendicular to the radius of the circle at the point of tangency. Now we can use that, so this idea, if we had it to draw in a right triangle. So they might tell us that the radius of the circle is, I don't know, 5, you want 5? And that this is not drawn to scale, but it is 8 units in length. Huh. So what is this? Okay, if this radius is 5, what is the length of this radius? 5. So that whole segment would be 13, so x is 12. Okay? So we might see something like that. Now, when we have tangent from an external point, we have these two that are tangent to the same circle. And when they're tangent from the same point to the same circle, then this segment here must be congruent to that. Do you remember that? Okay. Now, those of you that I've taught before, I'm about to throw a blast from the past at you. Do you remember our circle review from last year? All things circle. Okay, if you don't, we're about to go over it again. You blocked that out of your memory.
I understood on how to
It was bad.
No, circles are awesome. They are. Circles are fun. This is the part of geometry I enjoy. What part did I not enjoy? Can't remember the part I didn't enjoy.
Well, you're a math teacher. You should enjoy it.
That's not. I didn't enjoy non-Euclidean. I like Euclidean geometry.
It's like fun to think about.
Your brain's bigger than mine, then. All right. So this is the definition, just like what we talked about. This tells us the difference between a central angle. The central angle has the vertex at the center, and an inscribed angle. An inscribed angle has its vertex on the circle. An arc of a circle is just part of the circle. Now, with the central angle, the measure of the central angle is equal to the intercepted arc. So if this is 80 degrees, then this is 80 degrees. Now, with an inscribed angle, the inscribed angle is 1/2 the intercepted arc. So let's say this is 30 degrees. What would this be? Twice that, 60 degrees. And what if I threw this in? Threw in a central angle right here. What would the measure of the central angle be? 60, because the intercepted arc is 60. Good. Okay, do we remember central angles and inscribed angles? Great. Now, this is taking us back to chords. Here we have a chord AB and a chord CD. If these two chords are congruent, then their intercepted arcs must also be congruent. So when we're dealing with one circle, the same circle, if the chords are congruent, then the intercepted arcs must also be congruent. Or vice versa. If they told us the intercepted arcs were congruent, then we'd know that the chords were congruent. Okay, here is a diameter that is perpendicular to a chord. Or we could think a radius that is perpendicular to a chord. If they're perpendicular, then the chord is bisected by the diameter or radius. And vice versa. If it's bisected, then it must be perpendicular. And the way I used to see these problems on the SAT was, they would say, the radius has a measure of 10. I'm going to label this. AB has a measure of 8. What is the measure of CD? Okay, how could we do that? Well, I can draw a radius anywhere, can't I? And when I draw a radius, I've created a right triangle. I did not do this right. Let's change this to 16. Whoops! The radius has a measure of 10. Now that I've changed it, AB has a radius, has a length of 16. So what would half of it be? 8. So this would have to have a measure of 6. So if this is 6 and the whole radius is 10, what does it leave for CD? 4. Okay? So that's how they could take a problem, take some things we should know, and put it together. Okay. If we have congruent segments, then this congruent chords that are perpendicular, then this has to be congruent to that. Or if this segment KL is congruent to KN, then the chords must be congruent. Does that make sense? We can go either way. All right, on this one, let's see. This says angle A plus angle C equals 180. Well, angle A is this angle right here, isn't it? And it intercepts this arc, doesn't it? Y'all see that?
Yes.
Okay, angle C is this angle right here, isn't it? And it intercepts that arc, doesn't it? Well, together that's the whole circle, isn't it? And isn't an inscribed angle half? So what's half of 360? 180. So when we put them together, it has to be 180. Does that make sense? So when we add up opposite angles of a quadrilateral inscribed in a circle, opposite angles have to equal 180.
So opposite angles on the quadrilateral equal 180, but it can't be inscribed by a circle.
Yes, but both sets have to.
Those ones.
Okay. All right. Now we're going to do angles formed by segments. And first we're going to have segments inside and then segments outside. Okay. For a segment inside, this angle that is formed by these two segments is going to be equal to half the sum of the intercepted arcs. Now this point is not at the center. If it was at the center, it would be a lot easier. But it's not at the center. So A is going to be half the sum. So they can give it to us a couple ways. They could tell us this is 40 and this is 60. What is Y? It'd have to be 20. Not drawn to scale. I was just making stuff up. But that's how that would work. All right, this one, this angle, ABC, is going to be half the intercepted arc. So if this was 120 degrees, what would the measure of ABC be? 60 degrees. All right, this one, outside. An outside angle is half the difference. So it's the big arc minus the little arc. Half of that gives us this angle. An outside angle is half the difference. An inside angle is half the sum. Outside, half the difference. Inside, half the sum. All right, and either way, whether we have two secants or a secant and a tangent, it's half the difference of the intercepted arcs.
It's two tangents, is it still?
Two tangents. That one makes something different. But it should, yeah. Should still be. Okay, now let's do just segments. These were angles formed by chords, secants, and tangents. Now let's look at segments. When we have two chords that intersect, the product of A and B has to be equal to the product of C and D. Do you remember that? And on this one, the outside times the whole, A times A plus B, has to equal the outside times the whole, C times C plus D. The outside times the whole, well, they're the same. A times A is A squared, is equal to the outside times the whole, B times B plus C. And then the last thing are these two, arc length and area of a sector. This is the part of the circle, which is degrees over 360.
How is A squared
Times
equal
2
to
pi r.
B times B plus C? Like, clearly that's so much longer than that.
A squared is
I-
equal to B times B plus C.
I know, but
So
I
this
can't
is
even
degree,
see
it's just is. That's a just is thing now. We
C
proved it
is-
last year.
C is
Degrees
by
over 360 times 2 pi r is the arc length. Degrees over 360 times pi r squared is the area of the sector. Okay, I'm going to post this. This was just a note summary I gave to my students last year. I'm going to add this to the website if you want to print it out. And it's on, well, I had 2 extra spots and peace.
Circle frame.
All right. Make sure you do Unit 3. Come with questions tomorrow. Unit 3 is a biggie. Remember, the geometry portion of your end of course test is a large percentage of the question. So triangles, right triangle trig, and circles, highly important.